Our next speaker is Claudio Cacciari of SURF. His talk is entitled A Data Mesh for Research Data Management.
Okay, hello. I will not spend too much time on presenting me and my colleague because you have already seen my previous presentation and my organization, SURF. So I will go directly to the point of this presentation. So we, as SURF, as we have already mentioned in previous presentation, we are offering IRODs for different organizations and different institutions, and we see problem that is more and more recurring. The fact that we have project or community that want to share a single data platform, the IRODs, for example, or YODA in our case, across different projects or different team, different community. Ideally, since we have already various organizations that host IRODs on our system, on our infrastructure, we could share this data platform for multiple projects, but sometimes it's too difficult. There are two kinds of problems that we see. Organizational, so different organizations that need to collaborate in cross-organization project find difficult to find agreement in terms of policy, trust, who can access what, which people are authorized to access data on the other organization and so on. And technically, sometimes even convince the central IT of an organization to open a firewall, it's quite difficult. So in general, we see that various organizations and projects are struggling with this. And the workaround that we have been asked to do sometimes is to deploy another data platform based on IRODs for the specific project, which is possible, of course, but inefficient and expensive. So our question, what we were wondering is if we can improve this situation, how we can help our user, our organization to better share existing IRODs or YODA platform and services. So we think that a concept that has been elaborated in the business field can be helpful also in the research field, the concept of data mesh. In the business field, the data mesh has been called a decentralized data architecture that enable extraction of large-scale analytical data. We think same concept can be reused, let's say, in the research field, just changing a bit the definition, still a decentralized data architecture, but that enable the exchange of large, fair data. The important things is try to, as I said, avoid the need to create silos. So data platforms that are dedicated only specifically to a single organization or project. And so to avoid this, ideally the data mesh should allow to create a kind of virtualization of data in front of the data platform. So avoiding this duplication. Data mesh definition is based on 4 principles. Domain-oriented decentralized data ownership and architecture, data as a product, self-serve data infrastructure as a platform, and the possibility to have a federated computational governance. We will see in particular the first 2 are helpful to address our problem. So a domain-oriented decentralized data ownership and architecture indeed help in removing the fragmentation, so removing the silos. Because it supports the idea to provide it in a different way, aggregated per domain, per community, not per technology, not because you have already a dedicated service. Data as a product can be easily mapped, as a concept that can be easily mapped to fair, findable, accessible, interoperable, usable principle, as someone else, of course, not me, has already shown in literature. I just report here a table that show how it's possible to create the map. The main difference compared to this elaboration in the business field is that in the research field, the single node of a data mesh is not necessarily a single data set that has value, so a valuable chunk of data, but I would say it's an aggregation, it could be an aggregation of multiple data sets. So if we put all together what we have, the concept that we have defined and proposed so far, the idea is to have an architecture with a research data mesh, which is composed by multiple research data mesh nodes. Each of one is, let's say, in front of, on top of a data platform, like an Iris instance, for example, and is able to offer a slice of the data hosted in that data platform per domain or per project in a federated way, and lowering the threshold to assess the data for the team or for the user. And of course, in a fair way. So Iris or Yoda can be seen as a research data mesh node. This, in our opinion, could help or mitigate our initial problem of creating a data platform or data view, you would say, per project or community. And of course, this is not only a matter of technology. Yes, I have my specific technology, my data platform, my Iris. This is also an organizational effort because we said we want a federated governance on top of it. But the effort should not be so big, in our opinion. You just need to define the borders of this federated governance, this mesh space, leaving each partner in control of its own data. That's the important thing. We want to go a step further. So we, in our organization, have multiple data services. So Iris is one of them, but we have other. And we see that this happens also in other organizations. So we would like to generalize this approach in case, yes, you want to aggregate together multiple services, multiple data services in the same organization. So to deal with this complexity, we propose a hybrid mesh architecture, where inside the organization you aggregate the service using an hub and spoke architecture with a central hub that aggregate multiple services. And outside the organization, this hub and spoke is coupled with the mesh, the research data mesh. So hub and spoke become the node, the single node of the data mesh. This has the benefit that you can present the organization to the rest of the mesh, so the other organization or a large project, in a consistent way, because all the data policy and the data flow are defined through the central hub and spoke component. And yes, of course, we are aware that hub and spoke has consequences. Is a central point, so you could have bottleneck, single point of failure. Some of these, like a single point of failure consequence, can be mitigated with a good design. You can make hub and spoke redundant in terms of architecture and avoid problem with single point of failure. But in terms of bottleneck, indeed, we think to address the performance, the hub and spoke should only exchange the metadata, because every data flow can, in the end, be steered through the metadata. So applying policy in the central hub to just the metadata should be enough, also to make consistent all the data flow. While the data can go directly between, can be moved, transferred, exchanged directly between the data service. So in case of Iris, you can still directly move data through different Iris instance or Yoda instance, as far as the control is and the policy can be defined in the central hub and spoke system through metadata. So what is it in the end, this research data hybrid mesh node that I'm talking about? So what we propose here is that is defined with at least this 5 elements. It is a service registry because it needs to be aware of the service that are available in the organization and expose them, present them to the external mesh. It's a user registry because it's need to identify any actor that need to interact in the data flow to decide about the authorization, the permission. It's a metadata catalog because, as we said, we want to steer the data flow through metadata. It's an API gateway because it needs to route and control the API requests to the various service. And it's a data sharing point because, as we said, we want to advertise data through this, or we want to be able to exchange data, receive requests of data, and so on. We have started a prototype implementation that we call Neptune. It's a fast API server with a MongoDB. And it is indeed intended as the first node of a research data mesh. And it has a data model that is able to represent the data infrastructure with concepts like data provider, the service, data user, indeed the user registry. It is able to store metadata associated to provider or user or data itself, and as a concept of session, which are kind of represented as JSON documents that are transient in our system and help in exchanging the data. This is what you will see now if you query this prototype with, well, in this example, I'm querying the API with a client, a command line client called Surfy, which is just a wrapper around the API. And this is a service list with some metadata attached to them. You see, for example, an instance of Yoda that has the URL, the port, the protocol used to connect, or Lighthouse is an IROT system in our environment as a port, a protocol. You can attach, also define specific data space within a service like home, public, specific path, and so on. So a minimal set of metadata that should allow a client to understand how to connect to this. And you can have a list of users, so a user registry. Each user needs to have a single identity within Neptune, but you can have multiple accounts mapped to the various data services connected to the hub and spoke. So you have a mapping between the identity of the user and the different account that the user has. And this is stored there in Neptune so that you can steer data flow across different services, and Neptune automatically understand which account need to use. This is an example of metadata associated to an IROTS data provider. You can specify JSON document, and within the JSON document, a list of profile. So profile, list of attributes needed by a client to connect to the service according a certain protocol. Well, these are familiar for you, of course, IROTS attribute. You have API. This is convenient from Fast API. It's compliant to the Open API standard, offers Swagger interface to interact with it. And we have started to implement the data sharing part because you can indeed have endpoint to share data. In this case, for example, in this example, I'm sharing a data from my laptop, a file. What I got, what I get back when I share this is just a UUID. It's a unique identifier of a session, a JSON document within Neptune. And with another user, for example, call it Poseidon, I can download the data because the data are shared with other user. So if the data are shared, other user can download it. And that's the main point. I have also attached a paper to this presentation. So if you're curious, you can also see in more detail the concept that I've explained in these slides.
All right, thank you. Do we have any questions? Very interesting talk. I feel like I need to reread the slides to really let it sink in what you just discussed. But yeah, I guess if there's no questions, then thank you.